Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. Thank you very much. I'm Philip Emeagwali. At 10:15 a.m. New York time, Tuesday the 4th of July of 1989, the U.S. Independence Day, I experimentally discovered how and why parallel processing makes computers faster and makes supercomputers fastest. On that 4th of July of 1989, the first direct measurement of the fastest computation ever recorded across an ensemble of processors was recorded. On that 4th of July of 1989, I experimentally discovered that massively parallel processing supercomputers can solve computation-intensive problems that neither sequential processing supercomputers nor vector processing supercomputers can solve. My experimental discovery was about making grand challenge initial boundary value problems of extreme scale computational physics that are impossible to solve, possible to solve. I experimentally discovered how to massively parallel process the most computation-intensive problems in physics and how to massively parallel process them so that a time to solution of 30,000 years can be reduced to a time to solution of just 1 day. I discovered that 10 binary million or 10,485,760 fold increase and discovered that speed up across a new internet. I experimentally discovered that the new internet can de facto become a new supercomputer. I experimentally discovered how to reduce the time to solution of a grand challenge problem and reduce that time to solution across a global network of 10 binary million commodity off-the-shelf processors that are identical to each other and that are equal distances afar and apart, and reduce that time to solution so that computation-intensive problems that formerly took 30,000 years of time to solution will now take only 1 day of time to solution. I will identify in prose, not in abstract calculus, how my experimental discovery of massively parallel processing is rooted in the laws of physics that were discovered 3 centuries and 3 decades ago. I will describe how my invention of a new supercomputer is rooted in the technique of calculus that was also discovered 3 centuries and 3 decades ago. I will describe how my invention of a new internet, that is a global network of 64 binary thousand commodity processors, is rooted in the most computation-intensive set of floating-point arithmetical computations that arose from the most extreme scale problems in algebra that in turn arose from abstract initial boundary value problems of modern calculus. At its granite core, my experimental discovery is the new knowledge of how to massively parallel process and how to do so across a new internet that is a global network of 65,536 commodity processors, or a global network of as many identical computers. That experimental discovery represents a new way of looking at the computer. Parallel processing is the lodestar technology that makes computers faster and makes supercomputers fastest. The parallel processing supercomputer is a witness to global warming. The fastest supercomputer is the instrument that enables humanity to foresee otherwise unforeseeable climate changes. The modern supercomputer is used to foresee the future. On June 20, 1974, at 1800 Southwest Campus Way, Corvallis, Oregon, United States, I cut my 19-year-old supercomputer programming teeth on what some historians of the supercomputer described as the first supercomputer. In December 1965, that first supercomputer was the world's fastest computer. That first supercomputer was the first computer that could execute over 1 million instructions per second. I first had the idea of massively parallel processing in 1974, but I experimentally discovered massively parallel processing on the 4th of July of 1989. I first discovered massively parallel processing as the engine that powers the modern supercomputer, and I first discovered parallel processing in theory before I discovered it via experiments that I conducted across a new internet that is a global network of processors. Back in November 1982, my theoretical discovery of massively parallel processing was rejected at a scientific conference. That conference took place near the White House in Washington, D.C. On the 4th of July of 1989, the U.S. Independence Day, I experimentally discovered how to harness the potential supercomputing power of the 64 binary thousand commodity off-the-shelf processors of a massively parallel supercomputer that I visualized as a new internet and as identical to each other and as equal distances are far and apart from each other. I visualized that new internet as circumscribing a globe in a 16-dimensional hyperspace. My experimental discovery of massively parallel processing was ridiculed and rejected a dozen times before it was accepted in 1989. It was first accepted by the Computer Society of the Institute of Electrical and Electronics Engineers, called the IEEE. I began supercomputing with scalar processing technology, and I began 16 years before the Institute of Electrical and Electronics Engineers accepted my experimental discovery of massively parallel processing. My sequential, vector, and parallel processing supercomputer research notes date all the way back to June 20, 1974, to the Gaussian elimination algorithm of numerical linear algebra that I coded in BASIC and Fortran languages, and that I coded in my one-room apartment at 195A South Knox Street, Monmouth, Oregon, United States. My supercomputer research notes from the 1970s and 80s are posted at Emeagwali.com. The essence of my technological quest was to experimentally discover the new knowledge of how to increase supercomputer speeds and how to record the world's fastest speeds via massively parallel processing and recording them across a new internet that I visualized as a global network of 64 binary thousand commodity processors, or a new global network of 65,536 tiny identical computers. Metaphorically speaking, my quest was to scale the supercomputing summit of the Mount Kilimanjaro of the unexplored world of supercomputer knowledge. Mount Kilimanjaro is the tallest mountain in Africa. That Mount Kilimanjaro of computer science was the then unknown world of massively parallel supercomputing. My experimental discovery of the massively parallel processing supercomputer began as a blasphemy. Back in the 1980s, the 1,057-page report on the new supercomputer that I invented was severally mocked, ridiculed, and rejected. At 10:15 a.m. New York time, Tuesday the 4th of July of 1989, the US Independence Day, I arrived at that terra incognita, and I did so via a primordial internet. I arrived at that unknown world by forging a path never taken before. I arrived from a narrow footpath that was never taken before. I arrived at the terra incognita of supercomputing knowledge and arrived holding a small lantern that was dimly lit that I will use to read from a secret book that contained the knowledge of how to make massively parallel processing work, and do so at a time it was considered impossible to do so. The iconic image of the internet is that of a billion computers that encircle a planetary-sized globe, the Earth. From the perspective of an alien inside a spacecraft that is orbiting around the planet Earth and orbiting a few million miles away from the Earth, the atmosphere of the Earth is only as thin as the skin of an apple, and the Earth is the size of an apple. And the internet will seem like a planetary-sized electronic cloth that enshrouds the Earth with computations and communications. My visualization of the planetary-sized internet that I theorized in the 1970s was comprised of 65,536 commodity processors that were identical to each other and that were equal distances afar and apart, or that comprised of as many tiny identical computers. I visualized my 65,536 commodity processors as simultaneously computing to solve 65,536 initial boundary value problems of calculus that each arose from extreme scale computational physics. I visualized those 65,536 commodity processors as synchronously communicating the answers at the new time step and the new interior boundary conditions of the as many initial boundary value problems of computational physics. I visualized those 65,536 commodity processors as equidistantly separated from each other or separated by an area of 3,000 square miles afar and apart. I experimentally discovered how to harness the slowest 65,536 processors and harness them in parallel and harness them to compute faster than the fastest vector processing supercomputer ever built. I did the unimaginable and visualized an ensemble of 2 raised to power 64 power processors as the building blocks of a new supercomputer, and I visualized them as around the surface of a globe in a 64th dimensional hyperspace. The analog in the 16th dimension was my metaphorical image of my small copy of the internet that encircles the earth. That small copy of the internet was what I theorized and programmed to record unrecorded supercomputer speeds. It made the news headlines in 1989 that an African supercomputer wizard in the United States had won top prize in computing and won the award for recording previously unrecorded speeds in both arithmetical computation and email communication. I, Philip Emeagwali, was that African supercomputer scientist that experimentally discovered that the impossible to compute is, in fact, possible to compute. My experimental discovery of the 4th of July of 1989 of how to parallel process or how to compute simultaneously and how to compute at 65,536 commodity processors and how to communicate synchronously and how to communicate across 1,048,576 commodity email wires was the breakout moment of my 15-year-long quest for the parallel processing technology that makes computers faster and makes supercomputers fastest. That experimental discovery was the breakout moment for my invention of how and why to use that new massively parallel processing supercomputer knowledge and use the technology to build a new supercomputer that encircled a globe and encircled it in the manner the internet encircled a globe. That experimental discovery opened the field of parallel processing supercomputing. That experimental discovery is the defining moment of the supercomputer industry. My theory that parallel processing is not a waste of time was rejected and mocked in the 1970s and 80s. In November 1982, I gave a public lecture on the fastest supercomputers, and I gave my lecture to research computational physicists and to research computational mathematicians. I gave that lecture on parallel processing supercomputing, or solving 65,536 problems at once instead of solving only one problem at a time. I gave that lecture at a scientific conference that took place in an auditorium that was a short walk from the White House in Washington, D.C. Like most scientific conferences of the 1970s and 80s, I stood out as the only black and the only African attendee and speaker. Back in 1982, I also stood out as the youngest and as an emerging expert on how to solve the most extreme scale problems that arose from computational physics codes and how to solve those problems across my then theorized internet that was a global network of 65,536 commodity processors that were married together by 1,048,576 commodity email wires. I visualized that global network as one seamless, cohesive unit that is a new internet by definition, but not a new supercomputer de facto. At that extreme scale computational physics conference of November 1982 near the White House, I was the least known computational physicist, and for that reason, I was scheduled to speak last. But when I stood up to speak, every computational physicist except one stood up and left the auditorium. Fast forward 7 years to shortly after the Christmas of 1989, when the Computer Society of the IEEE, that is the world's largest computer society, issued a press release that I, Philip Emeagwali, had achieved a breakthrough in parallel processing supercomputing. On February 28, 1990, the San Francisco office in California of the IEEE formally introduced me to the world of computing. I was introduced at an award banquet of the largest international computer science conference. That computer science award banquet took place in Cathedral Hill Hotel in San Francisco, California. Ironically, at that award banquet, my wife and I sat next to Mr. and Mrs. Gene Amdahl of Amdahl's law fame, the most infamous law in supercomputing that was formulated by Gene Amdahl and formulated 23 years earlier and formulated back in April 1967. Gene Amdahl had hypothesized that it will forever remain impossible to parallel process across a supercomputer that is powered by 8 processors, and that it will forever remain impossible to record a speed increase of a factor of 8 and record it while parallel processing across those 8 processors. For me to record the maximum computation speed required that I squeeze every ounce of floating point arithmetical computation on each of my 2 to the power 16 or 65,536 commodity off-the-shelf processors. For me to record the maximum computation speed required that I squeeze every ounce of email communication across my 16 times 2 to the power 16 or 1,048,576 bidirectional email wires that I will use to email my computational physics codes and to email my intermediate answers and to email them to and from unique and unorthodox 16-bit long email addresses, each with no @ sign or .com or .something suffix. Each email address was a unique string of non-decimal 16 zeros and ones. Emailing across that new internet was unforgiving. No mispositioned zero within the entire email address space of 1,048,576 zeros and ones is allowed. I had to encode one binary million zeros and ones and encode them correctly, and I had to know their topological positions forward and backward. How did I make the impossible to compute possible to compute? The answer is that I indirectly made the impossible possible, and I did so by memorizing its 16 mutually orthogonal directions in 16-dimensional hyperspace instead of memorizing its 16 times 2 to the power 16 or 1,048,576 bidirectional paths. I indirectly made the impossible possible because the processors and the email wires of my new internet had a one-to-one correspondence with the vertices and the bidirectional edges of the hypercube in the 16th dimensional hyperspace. I indirectly made the impossible possible because I mathematically discovered that each processor knows its 16 nearest neighboring processors that I named quote unquote brother processors and knows them by their common 15-digit last name. That is, between 16 brother processors, their first names differ in only 1 bit out of their 16-bit long names. For me to record the maximum supercomputer speed that I recorded on Tuesday the 4th of July of 1989 that made the news headlines required that I first and foremost know all the nooks and crannies of my ensemble that is a new internet de facto. By definition, new knowledge must precede an invention. New knowledge of how to massively parallel process and how to solve the toughest initial boundary value problems of modern mathematics and extreme scale computational physics, and how to solve them in parallel, preceded the invention of the new computer that parallel processes and that is a new internet de facto. The reason my invention of a new supercomputer was ridiculed, mocked, and rejected in November 1982 was that it was an invention that was based on new truths that were deeply uncomfortable to conventional vector processing supercomputer scientists that were from the old school and that held on to their false beliefs on the validity of Amdahl's law that was formulated 15 years earlier, back in April 1967. That new knowledge was knowing how to send emails that I imagined as having 5 subject lines. That new knowledge was knowing how to send each email and how to send it at the end of each cycle of computation and communication of my ensemble of 65,536 initial boundary value problems of modern calculus and extreme scale computational physics. That new knowledge was knowing my global network of 1,048,576 email wires that I visualized as tightly circumscribing the hypersurface of a hyperglobe in a 16-dimensional hyperspace. I experimentally discovered that new supercomputer when I succeeded in simultaneously sending and synchronously receiving my intermediate answers at new time steps and doing both across my global network of 65,536 processors that is a new internet. My moment of experimental discovery was 10:15 a.m. the 4th of July of 1989. At 10:15 a.m., I witnessed the birth cry of a new computer that is a new supercomputer and a new internet that is outlined as a global network of 65,536 processors. That was the moment we changed the way we look at the supercomputer. That was the moment that for the first time ever, an ensemble of the slowest processors computed together and computed as one seamless cohesive unit and computed faster than the fastest supercomputer. That was my eureka moment because of the total speeds of my computations jumped from one computation at a time to 65,536 computations at once. That was my eureka moment because my floating point arithmetical computations jumped from 47,303 calculations per second per processor that I massively parallel processed through and to the world record 3.1 billion calculations per second that I recorded across my ensemble of 65,536 processors. For me, Philip Emeagwali, it was a visceral moment because it was an extraordinary world record in supercomputing that I achieved through the massively parallel processing supercomputer technology that was ridiculed, mocked, and rejected by the vector processing supercomputer community, and that was dismissed as a waste of time. I experimentally discovered how to record new speeds in email communication and how to increase those speeds by a factor of 1 binary million across 1 binary million email wires. The paradigm shift was from computing and communicating in the singular to doing both in the plural senses, I experimentally discovered how to solve the toughest problems in extreme scale computational physics and computational mathematics. I mathematically discovered how to solve those computation-intensive initial boundary value problems, and I discovered how to solve them at a supercomputer speed that is 65,536 times faster than a computer speed that is powered by only one processor that is not a member of an ensemble of processors. I mathematically discovered how to solve the toughest problems in modern calculus, and I discovered how to solve them across 2 to the power 16 commodity off-the-shelf processors that were identical to each other and that were equal distances afar and apart from each other, and that were outlined and defined by a new internet. I experimentally discovered a new internet that enables me to simultaneously send 65,536 email messages and to send them at a speed that is up to 1 binary million times faster than one-to-one email messaging that was sent from one processor to only one processor. I simultaneously sent and synchronously received my 64 binary thousand email messages, and I sent and received those emails across a global network of 16 times 2 to the power 16 email wires that outlined my new internet and defined that new internet as a global network of 64 binary thousand commodity off-the-shelf processors. That new internet is de facto a new supercomputer. For the 6 months onwards of the 4th of July of 1989, I cried each time that I successfully repeated my massively parallel computation and communication, and I cried each time I recorded speeds in computation that were previously unrecorded by any supercomputer. I cried because I had experimentally discovered how to marry an unconventional technique, namely computing many things at once, to an unorthodox technology, namely massively parallel processing across a new internet. I cried because I had experimentally discovered a new supercomputer, and discovered it when every vector processing supercomputer scientist believed that massively parallel processing was impossible. The Computer Society of the IEEE issued the press release of late 1989 that said that I had won the top prize in supercomputing. That IEEE press release put me in the news and led to cover stories in trade journals. I was in the news headlines for experimentally discovering how and why parallel processing will enable most computers and all supercomputers to record a speed increase of a factor of 65,536 or more. That experimental discovery that was in the June 20, 1990 issue of the Wall Street Journal is the reason every supercomputer is now powered by parallel processing technology. I was pleased to see parallel processing receive international recognition as the most important branch of computer science. Parallel processing technology has rich and fertile consequences. Prior to the 4th of July of 1989, the practical extreme-scale supercomputer applications of massively parallel processing was very limited. Parallel processing had limited applications in part due to the false belief in the Amdahl's law limit and due to the false preoccupations of the 1960s, 70s, and 80s that parallel processing will forever remain a huge waste of everybody's time. Today, all supercomputers are powered by massively parallel processing technology, and all computers parallel process across processors. And that widespread acceptance is the final confirmation of my experimental discovery of parallel processing.
Insightful and brilliant lecture.